by generation of carbanion, by creation of carbanion on particular carbon atom, some of the non-aromatic molecules we can convert to the aromatic moiety. Okay, so this is very important point. So, okay, the next point, that stabilization by a non-adjacent p bond. Okay, so this is some advanced thing that we can say that how to stabilize the carbanion. Okay, so these are the bicyclic compounds, and this bicyclic component, bicyclic moiety, bicyclic compound. Okay, so this is bis 2 to 1 bicyclic compound, whatever ketone, camphor, whatever is that one. So with bicyclic component, if we will treat that one on the with strong base, that one is generating carbanion, and there is a formation of okay, neighboring group participation is there, and like that things that one is happening. So now non-adjacent p bond, this is not adjacent, this is carbonyl group, that one is not adjacent to this negatively charged carbanion. So this is non-adjacent, still that one is helping to stabilize the negative charge. Okay, so if you will see, ions in which a negatively charged carbon is stabilized by carbonyl groups two carbons away are called homoenolate ions. Okay, so the stabilization we can carbanion can achieve the stabilization by the non-adjacent p bond as well. So this is some advanced thing that I thought I have to include in our things. Okay, now the basicity of carbanions. So we'll go for the basicity of carbanions. Okay, so here I have taken one example, that carbanion is there, trialkyl carbanion, and we do treat that carbanion with ammonia. Okay, so you know that carbanion and ammonia, the structure is isoelectronic with each other. Okay, these structures, they are resembling with each other. Now I have what I have this, how the carbanions acts as a base, that we are going to learn in this slide. See, we have discussed the things like carbanions. Once we generate the negative charge on the carbon atom, like if we will take example of Grignard reagent like CH3 MgPr. So CH3 carbon possess negative charge, and once carbon possess negative charge, it possess the it shows the high basicity. Okay, that is the, it's very strong base. Grignard reagent, very strongest base, having pK value residing in between 35 to 40. PK value of Grignard reagent is in between 35 to 40. So on the basis of pK, we can say that that one is the strongest base. As that one is strongest base, it can abstract proton from any molecule. Okay, so it's very highly reactive, highly strong base, and that can abstract proton from any of the moiety, or like Grignard reagent, like lithiated reagent. Okay, lithium containing components, that those things also, lithium having positive charge and carbon bearing negative charge. So pay attention that whenever you are using any reagent in organic chemistry in which the carbon possess negative charge, so that one is the highly basic in condition. Okay, so here is the, we do discuss the basicity of carbanions, basicity of Grignard reagent, basicity of lithiated reagents. Okay, so these Grignards and lithiated reagents, they are highly basic because the carbon do possess the negative charge on the carbon. Okay, that moiety. So that's why here we have taken the example of ammonia. Ammonia is base, but here carbanion is abstracting proton from the ammonia. So you can think that how much carbanion is more basic. Okay, so here ammonia acts as an acidic species and carbanion acts as a basic strong base. Okay, so ammonia, we do consider ammonia as a base, and if we will add carbanion to ammonia, so carbanion, due to presence of lone pair on carbon atom, these carbanions acts as the strongest base, and here ammonia acts as a acidic moiety. So in that way, this carbanion abstracts proton from the ammonia to form the whatever your methane or alkane, normal alkane, and we do generate NH2 minus, which is even strongest base. NH2 minus is the strongest base, and in that way we can explain the basicity of carbanions. Here we have explained the basicity of carbanion by reacting with the base ammonia. Okay, so pay attention that again I am repeating Grignard's alkali lithiated reagents. These are highly basic. Once carbon acquiring negative charge, that moiety becomes highly basic. Okay, so the carbanions has a negative charge on its carbon atom, making it a more powerful base and a stronger nucleophile than amine. Okay, so the carbanion is sufficiently basic to remove a proton from ammonia. So this is the achievement of carbanium, that it can defines carbon how carbanion is basic than the ammonia. Okay, next thing. Now, alkyl carbanions and pi stabilized carbanions. Now, we have to compare basicity and nucleophilicity of the carbanion. How we can, if there is very thin line in between basicity and nucleophilicity. Okay, so the some of the components which they can act either base or nucleophile. Okay, so same compound it cannot act as a good base or good nucleophile. Okay, so if negative charge is residing on any carbon atom, then we cannot say that negative charge containing that species it will act as a base, or we cannot firmly say that one will act as a nucleophile. Okay, so we have to go for the pK value and everything, and we have to compare whether that one is nucleophile or whether that one is a base. Okay, it depends upon different factors. Here I have explained some of those factors. Now I have taken the example of alkyl carbanions, started from the methyl carbanion, then one of the hydrogen replaced by one of the alkyl group, then two alkyl groups I have added, again three alkyl groups I have added. So now we can see over here, once we have added three alkyl groups, that means plus I effect has increased. As you know, plus I effect has increased, their stability of that carbanion is getting decreased. Okay, so stability of that carbon is getting decreased, so this one stability is decreased, so nucleophilicity decrease. As stability decrease, nucleophilicity decrease, and basicity has increased. So carbanion which possess three alkyl groups, that means strong positive I effect, due to that strong positive I effect, that one is acts as the strongest base but weak nucleophile. Okay, so if that one is acts as the strongest base, like just we have discussed Grignard reagent, if trialkyl Grignard we did use, so that one acts as the strongest base but weak nucleophile. Okay, so there is a relation in between basicity and nucleophilicity. If any moiety acts as the strongest base, eventually that moiety will act as a weakest nucleophile. Okay, so strong base, weak nucleophile, strong nucleophile, weak base. Okay, so this is the equation we can set like that. So here plus I effect got increased, so stronger proton abstractor, that means plus I effect makes that carbanion more basic and less nucleophilic. Then steric hindrance increases, that we know, so we have to compare which one is more basic and which one is which one is more nucleophilic. Now next one, pi stabilized carbanion. Okay, so in one moiety we have added alkyl groups, simple alkyl groups like methane, like methyl group, like ethyl group, like isopropyl groups, that those things we have added. Now we will add the aromatic things, that means aromatic rings like phenyl rings. Okay, so we will go on increasing the phenyl rings 1 2 3 4. Okay, so and we will see how is the basicity and how is the nucleophilicity. So very simple. Nucleophilicity, pay attention again, nucleophilicity and basicity, they are totally opposite to each other. As we will increase basicity, obviously the nucleophilicity will decrease, and if we will increase the nucleophilicity, obviously the basicity will decrease. Okay, so now in methyl carbanion, methyl CH3 minus, In that one, this is neutral. If we will add one phenyl ring on that methyl carbanion by replacing one hydrogen, again we have added one more phenyl ring, that means two phenyl ring is present. And finally, if we will replace all three hydrogens and if we will add all three phenyl rings, then we can say that the due to these as phenyl rings, they are impart minus I effect, they are electron withdrawing groups, and electron withdrawing groups, they gives stability to the carbanion. Okay, so due to presence of three negative, three C6H5 groups, these carbon is getting more stable, as those are three groups are electron withdrawing. So here basicity is getting reduced. Okay, so basicity is getting reduced because this negative charge is not no more available to abstract proton. Okay, so very simple thing. When you will abstract proton, NaOH is abstracting proton. NaOH is acts as a strong US base because on OH negative charge is present on OH minus. That means OH is minus. So negative charge is present on OH minus. So that's why it can abstract proton very easily, because OH minus charge is localizing on OH group. Here, negative charge on triphenyl carbanion is not present on this carbon atom, because that one is always delocalizing in between these three phenyl rings. So that's why, as that one is not available on these carbon atoms, it acts as a weak base. And as that one is acts as a weak base, it acts as a nucleophilicity also decreases. Okay, so reduces basicity. That one is also basicity also got reduced here, and nucleophilicity also got reduced here, also due to steric hindrance also. So this carbanion, it cannot act as a strong base, as well as it cannot act as a strong nucleophile. So intermediate things are there, maybe it can act as an intermediate nucleophile, like that, but we didn't see average nucleophile or like that. We have seen just which is strongest base and which one is the least basic. Okay, so here electron donating groups containing carbanion acts as the strongest base, but electron withdrawing groups are present there, then we can say that carbanion is weakest base, and it reduces basicity due to the non availability of that carbon atom. Okay, so now the next thing. Okay, this is not. So we'll stop here now. This is the